Okay, we're going to continue on here, chapter 14. So we've been talking about in this chapter basically liquids and the idea of water and how it changes phases and other substances as well. So remember, as we saw last time, there's a certain amount of heat required to do certain transitions of substances. So for example, that is the delta H of fusion or the heat of fusion. And that's the energy required to change the phase of a substance from solid to liquid and liquid back to solid. And remember that this happens at the normal sort of melting point or freezing point for a particular substance. So the amount of energy required to do that is the same, regardless of which way you're going. The only difference is really the sign, and that would represent either an endothermic process or an exothermic process. And remember, as we go from solid to liquid, that's an endothermic process, which means that would be a positive value for the delta H of fusion. And exothermic, as we go the other way, we have to get rid of all that heat and energy. So that would be a negative one. So something like water, for example, is something like 6.02 kilojoules per mole, or roughly 335 joules per gram. And again, that is the amount of energy, not to change any temperature or anything like that, but just to simply change the phase. And as we talked about, it also happens at its boiling point as well. And there's a certain amount of energy to do sort of that transition that we see at the boiling point, which is the delta H of vaporization. And that's the energy needed to go from liquid to gas and backwards as well. Again, it's going to be a positive number as we go from liquid to gas. It's endothermic, and again, a negative number as you go backwards, roughly for water, for example, it's about 40.7 kilojoules per mole, or roughly 2260 joules per gram. So if we were going from liquid to gas, which is the process of evaporation or vaporization, it would be a positive 40.7. If we were going backwards, gas to liquid, it'd be a negative 40.7. Again, that energy. Once again, here we would not be changing any type of temperature. We'd just simply be taking, for example, water at 100 degrees in the liquid state to water at 100 degrees in the gas state. So just simply changing the state. So we saw sort of a heating and cooling curve, which kind of covered those things. Something like this temperature. So right here, say at 0 degrees Celsius, if it was water, and right about here, which is a normal boiling point, 100 degrees Celsius for water. We also saw that these transitions here, it does definitely take a lot more energy to do that transition as you go from liquid to gas. Again, because we're kind of completely breaking everybody apart from one another and also bringing them back together as well. Remember, though, that if we are, and this is where it ties in sort of that earlier chapter we did, if we're doing something where we are actually in the same phase, but we are changing the temperature, that is where our specific heat comes into play. So again, on this curve anywhere here, that is basically ice or solid. This is liquid water, and that would be steam or gas. Anywhere in this sort of region where we're rising, they are all in the same phases. So in those regions, we would go back to our specific heat equation that we used earlier on in the semester. A couple of things that we did talk about as well, and we did an example. You do want to make sure, again, that you get the correct specific heat capacity, especially if you're doing something like we did in that example with water. Water obviously has the 3 different phases, so the different phases will have different values for the specific heat capacity, so it won't always be that 4.184 number if it's not liquid water. So you want to make sure you get the right specific heat sort of number to use. The other really important thing is, like normal, you want to make sure you know your final temperature minus your initial temperature, because that's really where you'll get a negative number or won't get a negative number. So you always want to make sure you kind of take that final minus initial. And that's really important as well, because if we were going like we did in that example from here to here to here to here to here, you can figure out the total energy, because they are state functions, by just adding up all those steps. So the energy required for each of those steps, like we did in that example at the end, I think, will give you that total amount of energy to, for example, take the ice to steam. If you're going backwards, starting from steam back to ice, again, the only difference would really be the sign. The numbers would be the same all the way through there. Any questions on any of that stuff we talked about? Yeah. I would say the one that they want you to know as you go through is definitely a specific heat of water. So that 4.184 number, you definitely need to know. And remember, it's also 1 calorie per gram per degree Celsius, which is the calorie conversion. And that is the calorie to joule conversion. That 4.184 joules is a calorie. So that one they definitely want you to know. I would say ice, because a lot of times people do examples with water, the ice and the steam one might be a good one to secondarily know. And that's not too bad, because they're both about 2. You know, one's 2, one's like 2.03. But definitely that 4.184 number they want you to definitely know. Yeah. Other questions? And as we also talked about, I think the other day as well, if it is not water, then obviously you need to look up different values, and they would also have different boiling points and melting points, right? If it's a different substance. So it won't always be 0 and 100. That's again specifically for water. Other questions on that? Okay. Now let's continue on here with this chapter. We're going to talk officially here about the forces within a molecule, and more specifically forces between different molecules. The first type of force is an intramolecular force. And intramolecular force means within the molecule. So this is basically within the molecule. And it is the force that basically holds that molecule together. So as we touched upon in other chapters, since we don't go in order here, that would be, for example, the covalent bonding here that we see within one water molecule. So that is the sharing of electrons between the oxygen and the hydrogen here, which would be an intramolecular force. If you're talking about an ionic compound, that is the electrostatic force, right, between the different ions that's holding those together. Intramolecular forces, either ionic or covalent, basically bonding, are those forces that hold one individual sort of molecule together. They are probably the strongest that you can have. So they are definitely much stronger than really the other type of force we're going to talk about, which is the intermolecular force. Intermolecular forces are the forces that hold one molecule together with another. So that would be the force that holds, for example, one water molecule together with another water molecule. Now, all intermolecular forces are weaker, again, than any intramolecular force. And I think we might have talked about it before. We could see that with water as an example. Obviously, the individual covalent bonding here are intramolecular forces. Intermolecular forces is this bonding here between the two water molecules. And we know that when we do heat something like water up, really the first bond that breaks is that bond between the different water molecules, which allows, say, liquid water to go off again into that sort of gas phase. If the opposite was true, again, if the intramolecular forces was much weaker, if this intramolecular forces were weaker, what we would see actually is the breaking apart of these bonds within each individual water molecule, which would create a lot of havoc there. It would produce a lot of hydrogen gas, oxygen gas, and clearly that doesn't happen, you know, when we go to boil our water to make pasta or something like that. So these intermolecular forces are always much weaker than any intramolecular force. So these intermolecular forces, weaker than intramolecular forces. The good thing about intermolecular forces is the basic way that they work is a pretty simple sort of attractive force. It is pretty much like electrostatic attraction. it pretty much is this basic positive side of one molecule. It's attracted to the negative side of another. So that is pretty much how all intermolecular forces basically work. Is there's a positive side to one molecule, negative side to the other, and that's pretty much the attractive force that they have. This sort of positive and negative is achieved by what we talked about in bonding, unequal sharing of electrons overall in the molecule. So it's because the electrons are not being shared sort of equally, they pile up on one side versus the other. That makes that side of the molecule more negative, the other side more positive, and now they have a way to interact with each other. Intermolecular forces are extremely important on a lot of things that we talked about in some other chapters. They are the reasons why certain things are soluble in each other, so that like dissolves like. And that is because things that have similar intermolecular forces will be able to interact with other molecules the same way that they interact with themselves, which makes them very soluble in each other. Also, why when you put things that have very different sort of intermolecular forces together, they have no way to maintain those interactions, and basically they are not going to mix very well, as we would talked about. So that's why polar things and polar things work really well, because they both are using the same intermolecular forces. Ionic and polar works really well as well for that same reason. Nonpolar and nonpolar, which is something sometimes, again, people miss in terms of solubility, work really well together because, again, they're using the same type of intermolecular forces. Again, only when you cross over that polar to nonpolar, you run into trouble because, again, they're using very, very different types of intermolecular forces. So what we're going to talk about here as we go forward is really intermolecular forces. Again, these forces between different molecules. So the first type of intermolecular force is a dipole-dipole interaction. And if you remember, again, dipole happens when a molecule has a dipole moment, usually. And a dipole moment is pretty much our polar molecules. So our polar molecules has a fixed dipole moment, like water, for example, or other polar molecules. And what that means is, again, the same thing we talked about in bonding. Overall, there's an unequal sharing of electrons in that molecule, which means if you have a polar molecule, you once again will always have a positive side of that molecule and always a negative side of that molecule because of the unequal sharing of electrons. That is sort of a fixed sort of charge that it has. No matter what you do to it, it will always carry like that positive side on one side of the molecule, negative side on the other. You do too much to it to screw it up. And that's why this is a relatively very strong sort of interaction, because they're always good to go. They always have a positive and negative side. So when two polar molecules get near each other, it works really well, because again, the positive side of one and the negative side of another are going to be attracted to one another, and they will pretty much bond pretty strongly. They are only a 1% as strong as covalent ionic bonds, and that is because covalent ionic bonds, as we just talked about, are intramolecular forces, so they're much, much weaker than that. But they are one of the strongest sort of intermolecular forces that you could have, and this is the main type of interaction that polar molecules use when they interact with themselves, and also when they interact with other polar molecules, is through dipole-dipole interaction. There's also another similar one, which is sometimes referred to as ion dipole interaction. Ion dipole interaction is when an ion and a polar molecule come together. So if you think about it, this is pretty much how an ionic compound dissolves in something like water. Water is polar, where the oxygen side is more negative, the hydrogen side is more positive. Again, it has a dipole moment heading in that direction, represented by that same arrow that we used when we talked about in bonding. So when we put something like, say, sodium chloride in with water, what happens again is the sodium ion and the chloride ion once again are attracted to water's different sides. So we have basically our oxygen, which is the negative side of water, attracted to the positive ion. We have our hydrogen, which is the positive side of water, attracted to it. And this is, again, as we talked about, really how we make a solution. This is how ionic compounds basically dissolve to each other, and it works really well. And this is sometimes specifically called an ion dipole. Ion because ions are involved, and dipole because we have a polar molecule involved. And that's the sort of interaction that we see when we dissolve some type of ionic solid. So dipole-dipole interaction, again, is a relatively strong interaction. It is the type that polar molecules use. And more specifically, it's the type that polar molecules that do not have the ability to hydrogen bond mainly use. So this is pretty much usually not ability to hydrogen bond. And we're going to talk about hydrogen bonding here in just a second. But usually this is the type of interaction for those guys that do not have the ability to hydrogen bond, but they're still polar. Any questions on? So here again is our dipole-dipole interaction. Maybe.
Activities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds. Therefore, it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So that's a good reminder of a couple of things. What we're talking about here when we talk about polar molecules, again, is molecular polarity. So again, the entire molecule as a whole, not just the bond polarity when we did the difference in electronegativity. So when we talk about a polar molecule here, it is looking at everything together, and the overall molecule, is it polar or nonpolar? Any questions on that there? So again, as you saw in that sort of animation and here in this slide, they will try to, when they come together, really maximize areas where positive and negative guys kind of get together, and minimize areas where positive, negative sides of molecules end up near each other. No matter what they do, they will always have sort of positive near each other and negative sides near each other. But they really used to kind of keep wiggling around until they do maximize more of that attractive force than the repulsion force, which is what we would have when we have same type of molecules our size together. Now, another type of dipole-dipole interaction, which is a really strong type of dipole-dipole interaction, is hydrogen bonding. So hydrogen bonding really is dipole-dipole, but it is sort of a category on sort of fall under the dipole-dipole umbrella. Hydrogen bonding is a really strong intermolecular force, and it is based on a bond between some highly electronegative atoms, where you have hydrogen that is directly bound to nitrogen, oxygen, or fluorine. So once again, if you look on the periodic table, nitrogen, oxygen, fluorine, those guys are upper right of the periodic table, which is where you have the highest in electronegativity. So when you have hydrogen bond to one of those guys, it's going to create quite a good polar bond and allow it to hydrogen bonding. That is what we see in water. Water has a hydrogen that is bound to oxygen in this case, making this bond really polar. And that is the bond that happens when, say, two water molecules get together. The oxygen of one is attracted to the hydrogen of another, so it's able to hydrogen bond. If we take something like methane here, which is CH4, Although methane, once again, has a ton of hydrogens, they cannot participate in hydrogen bonding for a couple of reasons. First off, carbon-hydrogen bond is nonpolar, which means there's no separation of charge. That overall molecule is also nonpolar, so there's no positive side or negative side. It's really kind of neutral. So again, just the presence of hydrogen is not enough for something to participate in hydrogen bonding. It does need to be directly attached that hydrogen to one of those three guys, which will allow it to participate in hydrogen bonding. So this guy will not be able to participate in hydrogen bonding, even though he has a ton of hydrogens that are there, because they're pretty much non-polar and not attracted to those other guys. We take a look at something like NH3. Can NH3 participate in hydrogen bonding? NH3 can participate in hydrogen bonding. It is a hydrogen directly attached to the nitrogen. It's also a polar molecule, so it would be able to participate in hydrogen bonding because of that. So hydrogen bonding is actually technically considered stronger than just a regular dipole-dipole interaction. It is the strongest sort of interaction that you can have. And that's why things that have the ability to hydrogen bond typically will have very high melting points and boiling points because they're held together very strongly. It's because of that strong attraction between the hydrogen bonding. It takes a lot more energy to separate them out, like at its boiling point where they need to go into the gas phase. And because it takes a lot more energy to do that, that results in a much higher boiling point. So if you ever ask a question about, boiling points, melting points, freezing points, those that can hydrogen bond typically have much higher than those that cannot in terms of that. Any questions on that there?
Some polar molecules have unusually strong intermolecular attraction called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with 2 hydrogen atoms and 2 unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6-membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So as we just saw there as well, that also again is an illustration of what we talked about with why ice is less dense than liquid water, as you saw there in the sort of ice version. Because of that hydrogen bonding, again, it creates all those big open spaces between the different water molecules, which means its density is much lower because it has a much larger volume. With the more energy that it has in the liquid phase, it doesn't lock into those big kind of open spaces. So those water molecules actually are able to kind of get closer to each other. And that's why water has an unusual sort of characteristic of being less dense in a solid phase than in, say, its liquid phase, which is very unusual for a substance. So hydrogen bonding really strong. Dipole sort of next in terms of strength, even though they're very similar to each other. Here's our hydrogen bonding happening between our different water molecules. So what does everybody else use? Everybody else after that sort of uses what is referred to as dispersion forces. Dispersion forces, sometimes all these things are called van der Waals forces or London dispersion forces. This is really where our nonpolar molecules basically use. So this is pretty much your strongest intermolecular force for nonpolar molecules. And dispersion forces are relatively weak forces that exist among nonpolar molecules that involve an accidental dipole or an induced dipole by a neighbor. So what does that mean? There's really a couple ways dispersion forces could happen. you can have a ion and a nonpolar molecule. You could also have a polar molecule and a nonpolar molecule together. And for the short period of time, this can produce an ion-induced dipole. And this guy could do a polar-induced dipole. And what that means is what's going to happen, for example, temporarily is either a positive ion or a negative ion comes near a nonpolar molecule, or a polar molecule is in the vicinity of a nonpolar molecule. We'll just take this example here. If this was the case, what would happen in this nonpolar molecule, which is pretty much neutral, is its electrons would decide to sort of head the other way, away from the negative charge of the polar molecule. And what would happen in that particular case is this polar molecule here will now make this nonpolar molecule that normally does not have a charge temporarily gain a charge. So it'll temporarily gain a charge as those electrons kind of move away from the negative side of the other. And now these two guys that normally do not have a way to interact with each other will temporarily be able to interact with one another until like the polar molecule kind of moves away or the ion moves away, and those electrons in the nonpolar guy is going to come back and sort of break apart. So that's why it's sort of a temporary sort of occasion that could happen, and it can be induced. This is also why, right, when you mix something like oil and vinegar salad dressing, it does mix for a bit, right? And it's able to kind of keep some interaction happening. But over the long period of time, what will happen again is everybody will separate out. And that's because the nonpolar guys have no way to kind of lock those interactions in and keep them for the long period of time. They're just going to be able to kind of separate out from each other. The other way that this could happen is what is sometimes referred to as an instantaneous dipole. So if you have two nonpolar molecules, what could happen because electrons are flying around is, in a certain case, all the electrons may end up, say, over here on this side of the molecule. They'll all go vacation on the left-hand side of the molecule. When it does that, that's going to create a temporary charge in this nonpolar molecule, which is still next to this nonpolar molecule. It's going to make those electrons in the second guy also go away, and they're going to reshift. And now these two nonpolar molecules that started out with no separation of charge have now temporarily gained a separation of charge, and they're able to interact with one another through that. This is what is sometimes referred to as being polarizability. Our polarizability is the ability of electrons to move from one side of the molecule to the other. Now, as soon as those electrons basically go back the other way, that interaction is going to break apart, new interaction is going to happen. So you can get this sort of back and forth sort of happening. And it's why it's really temporary and very, very weak, these type of interactions. These type of interactions here are the weakest that you could have. And that is because it relies upon something happening. It relies upon the electrons going one way or the other. It relies upon some type of thing with a charge to help the electrons go one way or the other. They are not good to go out of the box in terms of interaction because they're pretty much neutral. They have no positive side or negative side. So it relies upon this to happen. Polarizability increases with molar mass. So dispersion forces, people that use dispersion forces, that strength of this weak interaction actually increases with increasing molar mass. So the strength of this increases with increasing molar mass. So if I have more molar mass, the reason why this happens is if I have more molar mass, I have more atoms, I have more electrons. there's a greater opportunity for electrons to interact with each other and a greater opportunity for these electrons to really go one way or the other and sort of distort the overall electron cloud. So if you have to compare the strength of something that is used in dispersion forces to somebody else that's using dispersion forces, two nonpolar molecules, the one that has the higher molar mass is typically the stronger, weaker dispersion force. If that makes sense. Any questions on that? That is the main force that nonpolar molecules use. So that is why a lot of organic molecules, which are pretty much nonpolar, most of them, are gases and very volatile because they're held together by these very, very weak intermolecular forces, which means, again, it doesn't take a lot of convincing to get them into the gas phase. That's why methane, propane, butane, a lot of those early organic molecules, they're found in the gas phase. Also why, again, as we might have talked about, when you go take organic, they throw you in a fume hood because a lot of organic molecules are very volatile because they're held together by these really weak intermolecular forces, which means if you look at them wrong, they're just going to jump out into the gas phase and create vapor and stuff like that. And usually they're pretty flammable, which is why they also keep you in there as well. Any questions on that? So in terms of the strength of these intermolecular forces, the strongest that you could have, the strongest is hydrogen bonding, followed by dipole, and really the weakest of all of them is our dispersion forces. And that is because anything that involves hydrogen bonding, anything that involves dipole, these are things that are polar molecules, which means, again, no matter what you do to those polar molecules, because of the unequal sharing of electrons, they will always have a positive negative side, which means, again, they are always good to go to do the intermolecular bonding. Something that's nonpolar, essentially neutral, it relies upon something happening to it to allow it to interact properly. So again, that's why it's much weaker and much more temporary, as everybody else has a fixed dipole moment that is polar that will use either of those things. Any questions? So that's why earlier I said dipole is usually the one that's used by polar molecules that, again, do not have the ability to hydrogen bond. So for example, like the one that we saw, I think about the maybe like this, I think. This guy is a polar molecule, but does not have hydrogen, right? So it cannot hydrogen, it does have hydrogen, but doesn't have a hydrogen to hydrogen bond with. So it would use dipole versus hydrogen bonding. Our SO2 that was also in that little video there, again, does not have hydrogens to hydrogen bond with, but is polar. So we'll use dipole interaction. Any questions on it? 3 there. So here's a video of that.
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So again, as we saw there, it is that sort of event that occurs that allows everybody near that sort of distribution of those electrons start to interact with each other and through that dispersion forces. All right, any questions on intermolecular forces? All right, let's talk about a few more things here in this chapter. Evaporation and vapor pressure. Vaporization or evaporation, again, is what is happening at the surface of any liquid. At the surface of any liquid, you essentially have guys jumping out of the gas phase, slower moving gas molecules, jumping back into the liquid phase. And what happens, for example, why something evaporates, say if you have a drop on your desk or whatever it may be, eventually it'll evaporate because as it goes through evaporation, there's air that kind of blows away those molecules and prevents them from coming back into the liquid phase. And that's why, if you have like a little drop or something on the table, it will eventually evaporate. Takes much longer for evaporation to occur if you throw it into like a beaker, right? Because now only the guys on the surface are going to get blown away. There's still a lot of liquid underneath there, a lot less air is spread out than say a drop on the bench where it's happening all over and it could kind of escape. Also why when you put a lid on it, it's even longer, right? For something to sort of go away or evaporate. So the pressure of a vapor in equilibrium with its liquid is called vapor pressure. Because this rate of evaporation that's occurring, you will have gas molecules above the liquid, and gas molecules will create pressure, and that is really what the vapor pressure is. Liquids with high vapor pressure are said to be volatile. They will evaporate pretty quickly. And that is because if you have a high vapor pressure, the only way you can do that is you must have a lot of gas molecules above the liquid. And if you have a lot of gas molecules above the liquid, that means your liquid is evaporating at a relatively quick rate. And that's why they will go into the gas phase really easily. Again, like we just talked about there with those organic compounds, because they're held together by those weak dispersion forces, doesn't take a lot for them to escape into the gas phase. And again, while they're pretty volatile, the vapor pressure of a liquid is at a given temperature is determined by the intermolecular forces on it. The stronger the intermolecular force, the slower the vapor pressure you will have, because it's going to take a lot more energy for those molecules to escape the liquid and go into the gas phase, which means you'll have less gas molecules above the liquid. And you'll have a much lower vapor pressure because of that. Questions on that there? Now, we also see a liquid in a container. There's sort of a situation that occurs when you do put a lid on it. After you put the liquid in there at the beginning, you'll have, say, a liquid level right about there. What's going to initially occur is you're going to have a greater rate of evaporation that's going to happen. So you're going to have this rate of evaporation, which is going to pretty much just begin. And in this particular case, unlike sort of the liquid on the bench, it's got nowhere to go, which means those guys cannot escape it because you put a cap on it. That means that these guys are going to head back the other way, and you're going to get some rate of condensation going to occur as they drop back. Eventually, what will happen is both of those phases will actually come to equilibrium. And what equilibrium means is when they reach equilibrium, the rate of evaporation will equal the rate of condensation. And what you'll also notice is at that point, you usually will see just a slightly drop in the overall liquid component in that container. And that's because when you put it in there, there was no evaporation. But as soon as you put it in there, there's going to be some molecules that evaporate out. And then it's going to start coming back the other way. When we reach equilibrium, it doesn't mean, as the name might imply, that you have equal amounts, say, of liquid and gas happening. What it means is actually the rate. So just as fast as those guys jump out of solution, you have the same amount, or it's the same guys jumping back and forth. So you have this rate going back and forth that equals each other. And what that essentially will do is lock everybody into place in terms of where they are in terms of the level of the liquid that you will see, because just as soon as these guys drop, you'll have the same amount coming back out of solution. So there's a net no change is going to occur in the constant versus the liquid at this point. All right, so let's talk a little bit about some types of solids here to finish up this chapter here. Good talk. So there's many types of solids. A lot of substances are crystalline solids, and these are guys with very regular arrangements of their components. There's two types of crystalline solids: ionic solids, like sodium chloride, how all the ions come together in the solid phase. molecular solids like sucrose as well. Now, a crystalline solid, like an ionic solid, has really long-term order as to how it's in three-dimensional space. It has such long-term order that, you know, if you had all these ions together in their three-dimensional space, clearly not drawn three-dimensionally here, but they're all packed in there together. It is such an ordered arrangement that if you took just like a little slice of it, for example, of how those molecules or atoms are together, you can rebuild it just from like a little piece of it. And this is what is referred to as a unit cell. He'll talk more about it in 1A. But you could take like a slice of this sort of piece of solid, and just from that, you can basically just keep repeating that pattern and you can rebuild back to three-dimensional structure of, say, an ionic solid as to how they come together. So that is such a repeatable order that you literally can just take one little sampling of it and recreate it very easily. A third type of crystalline solid is an atomic solid, and that contains atoms of one type of element covalently bonded together, like graphite, boron, silicon, and all metals is how they sort of interact with each other. Metals interact with each other through electrons sort of vibrating around. That's how they kind of interact well with each other. So this is an ionic solid, and again, when they come together, it is a very, very ordered sort of method, obviously maximizing attractive forces between the oppositely charged ions and minimizing those repulsive forces between similar types of ions. This is also an example of the different types of solids here. We have diamond. We also have our ionic solid, and this again is how water comes together. And again, we could really see that in ice, all those big open spots as they come together. One's more of a layered type of situation, which is very common with solids. One is this very organized, ordered type of thing, and one is a pretty random sort of way that they come together in the solid form. Now, bonding in solids, in terms of ionic solids, they're held together by this really strong intramolecular forces, as we've been talking about, which means that they will definitely be very hard to sort of get into the gas phase because of that really strong attractive forces. That's why I think we've talked about a couple of times throughout the semester. You pretty much can heat the heck out of an ionic solid. It will not go into the gas phase because of how strong those intramolecular forces are. They typically also have very high melting points. They will actually again start to melt before they will go into the gas phase. Molecular solids are held together by these intermolecular forces, and they melt together. They melt at low temperatures. So really the difference here is intramolecular forces versus intermolecular forces. And that's why what we talked about when we talked about gases, that it's much easier to convert a molecular compound like water into a gas than it is to try to convert a compound like sodium chloride into a gas, because of the difference in how they're held together. Any questions on that there? Now, an alloy, in terms of metals, there's a couple of different types of alloys. An alloy is a substance that contains a mixture of elements and has metal type properties. A substitutional alloy consists of a host metal where some of the metals are replaced by atoms of different elements of similar size. So like sterling silver is 93% silver with some copper kind of poked in there. Interstitial alloy is formed where there's holes in how the metals are packed together, and we sort of put little metals into those holes between them, like steel contains carbon atoms in the holes of iron. So there's a couple of different alloys. Alloys, as you also learn in maybe like 1B, is a way that can sometimes protect metals by changing There sort of was known as their SRP or standard reduction potential to help prevent them from going through corrosion. So sometimes we do things like that, and it can really sort of protect metals in certain cases from going through substantial oxidation, just in a natural situation. Here's a couple of pictures of that. Again, you can see we have some substitutional atoms in here, and these little open spaces, we have little sort of atoms in its place. Any questions on that there? All right, that should wrap up chapter 14, I believe. All right, we are going off to 11 because we skipped over that. So we're gonna go here to chapter 11. And chapter 11 is really a long-awaited movement of chapter 11, really all about electrons. We're going to talk about electrons, talk about what happens as electrons transition from one energy level to the next. We're also going to talk about electron configuration, which we saw in a number of places as we kind of go out of order in the stuff in terms of chapters. So we'll talk about electron configuration and sort of how to write it properly through here. So first off, we talked about Rutherford's atom and basically described again an atom as having that positive core. It has those electrons that are again flying around in this pretty random sort of manner, as we'll talk about in this chapter. The nucleus is very small compared to the size of the atom. So remember that electrons are basically flying around in those empty space that we associate with our modern version of the atom. Electrons, as we'll talk about, can be on different energy levels. And a lot of what we're going to sort of discuss early on in this chapter is the idea of what happens as electrons go from, say, a lower energy level to a higher energy level. That's going to require some energy being sort of gained by the atom. But eventually what will happen is these electrons really want to be in a lower state of energy, so they will try to work their way back down to a lower state of energy. The idea of conservation of energy that we talked about in the previous chapters means that in certain cases, energy has to be given off by the atom to allow those electrons to transition back down, just like it would require a certain amount of energy to be gained by the atom to allow those electrons to go forward or upwards in terms of energy. So some of the early work done on this idea of energy and how energy sort of travels through space was done by a guy by the name of Planck. And Planck did a lot of work with atoms at various temperatures, and he noticed that they did emit energy only in whole numbers. And this idea that we'll talk about throughout this chapter is this idea of energy is sort of gained or released or given off in only certain whole number multiples of energy, which are sometimes referred to as a quanta of energy. So what does this mean? This means essentially the idea here is if I have an electron down here, it will gain enough energy to get to this energy level. It will not stop in between. Just like if this electron that started, say, up here, wanted to go back down to another energy level, it will lose the right amount of energy to do that. The idea of quantized energy is sometimes sort of similar to the idea of stairs. When we walk stairs, we find ourselves on this step, we find ourselves on this step or this step. We have enough energy to get to the first step, the second step, the third step. And same thing if you were going downstairs, you would have enough energy to go down from one step to the next. You don't typically, when you go up or downstairs, go, oh, it's going to kind of lay it up between steps, right? And kind of fall. And that's the idea of quantized energy, which is electrons will, as they are transitioning, will gain enough energy to fully transition one energy level, two energy levels, three energy levels, either up or down. They will never find themselves kind of hanging out between energy levels because that is not how the energy is either absorbed or released. It's kind of the same idea as well as a stair example. There's certain people that does one step at a time, right? There's some people could do maybe 2 steps at a time, right? Or 3 steps at a time, maybe not 4. That seems like a lot of steps. But there's certain people that have enough energy or the ability to sort of do that. And electrons, same idea. Again, they can transition one energy level, multiple energy levels, but they will fully transition and again, not find themselves kind of trapped between different energy levels. And that's the idea of quantized energy. Any questions on that there? Now, the development of Planck's quantum theory, we talk about radiation, and radiation is sort of the emission and transmission of energy through space in the form of waves. So there's this idea, obviously, as we talked about, of conservation of energy, which means we don't create nor destroy energy. So the energy has to go somewhere. So if somebody gains energy, we see electrons going upwards. Again, as they work their way back down, that energy has to leave the atom, go somewhere. It travels into the atom and out of the atom in the form of waves, basically. So we have energy basically traveling through space in the form of waves. And as we'll talk about here, these waves have some different properties. But a wave can be thought of as a vibrating disturbance, and with energy is transferred. The speed of the wave depends on the type of medium it's traveling in. The wave is moving, the bird is not. Yes, the wave is just kind of moving past him, right? And if you've ever been in the ocean, I imagine, and you've been hit by a wave, it has a lot of energy associated with it as it is traveling. And again, that is sort of how we visualize energy moving either into the atom or out of the atom, as bless you, as a result of electrons being transferred. As we'll talk about, this is really the idea of like what happens with fireworks, and we see different colors depending on the wavelength and where these waves come out. We may actually see colors sort of happen when that happens and these transitions occur. So let's talk about the different parts of the wave. There is the wavelength, which is sometimes abbreviated with a lambda symbol, and that is the distance basically between peak or trough. So kind of between here is our wavelength. Wavelengths are usually in meters, centimeters, or nanometers. I would say very common, all three of these, but meters and nanometers are used a lot. Nano is 10 to the minus 9, yes. So that is a conversion that we see a lot here. The frequency, which is abbreviated, not really with a V, which no, it's a nu. That is the number of waves that pass through a particular point in a given second. The frequency is usually in units of hertz or reciprocal seconds. So this relationship is important. 1 hertz is a reciprocal second, or 1 over seconds. The amplitude is the vertical distance from the mid wave to sort of the base there at the peak of the trough. And the speed of the wave can be found by taking the wavelength times the frequency, is basically how fast the speed is moving. So if we just look at units, if you take wavelength times the frequency, wavelengths is like in meters, frequencies in reciprocal seconds. So when you multiply them, you get a speed of a wave of something like meters per second is the speed that a wave is moving. Any questions on that there? That's like 10 to the minus 9, yeah. In a meter, right? So here's our different parts of it. Now, light behaves like electromagnetic radiation, which means the emission of energy in the form of electromagnetic waves. Now, electromagnetic radiation sometimes have properties or characteristics of particles. So a lot of what we talk about here in sort of this quantum theory sort of idea is the idea of wave particle nature of light. So it was found through experiments and ideas that particles like electrons, they characterize or have wave-like function, so they travel like waves. So particles sometimes travel as like packets of particles travel like waves. And waves will have particle-like function as well. So a lot of this dual nature of light can have a wave-like function and also a particle-like function as well. And it gives us some unusual, or gives us some properties of what we see, say what happens with electrons as it's around the nucleus. So we think of a beam of light that is traveling through as tiny packets of energy, which are called photons of light. So as these electrons are transitioning, say downward in energy, when they give off this energy, this is sometimes referred to as a photon of light. And that photon of light will have a specific wavelength. And as I mentioned before, if it happens to end up in the visible part of the spectrum, we will see colors. So that visible part of the spectrum, again, is where we see colors like red, orange, yellow, green, blue, indigo, violet, the Roy G. Biv. Not all transitions will result in photons of light coming off in that visible part of the spectrum. They may come off in any part of the spectrum where we might not see color of light, but maybe we'll feel heat or energy coming off if it's in the infrared sort of spectrum. The wavelength of light, the longer the wavelength, the lower the energy and the lower the frequency. The shorter the wavelength, the higher the energy and the higher the frequency. So if we have a wave that's traveling through space like this, it has a much longer wavelength, which will have a lower energy and also a lower frequency, as opposed to a wave that has a much shorter wavelength, which means that it will have a higher energy and a higher frequency. Just think about it, it's like moving really fast versus one that's just kind of moving through space pretty longly there. So that's an important relationship between wavelengths and energy. Again, longer the wavelength, lower the energy, higher the wave, smaller the wavelength, higher the energy associated with it. So here's a light wave of yellow. It can be thought of as, again, a packet or stream of energy like particle, and also will have sort of a wave-like function happening with it. Here we see red versus blue. So even within colors, there is a difference in energy here. And we would see that in terms of red, it has a longer wavelength, which means it will have lower energy than our shorter wavelength here of blue. So when you think about that Roy G. Biv, that red, orange, yellow, green, blue, indigo, and violet, the violet side, purple side is a much shorter wavelength, and it's actually higher in energy than red. And what does that mean? You could actually make some predictions, for example, in terms of when you see a color come off, for example, you see red versus, say, purple. Red would indicate a lower energy transition, which means when we're talking about electrons, that could be an electron just going down one energy level, would be less energy than, say, an electron that had to come all the way down, say 3 or 4 energy levels. So the guy that had to travel much more in terms of energy levels would require a lot more energy being given off, and that would result in actually a smaller wavelength, more on the, say, the purple side, than the guy there that just traveled one energy level down, not as much energy difference, which means it would have a longer wavelength, maybe closer to the red side. So even when you see colors, you can make a pretty good estimate in terms of maybe when we talk about electrons transitioning, you know, how much of a transition is happening. Some common features to all electromagnetic radiation and waves is the speed at which they travel, and that is 2.9979. That is the number they want. So I think your note says 3 times 10 to the 8. So they want you to memorize this number instead, which is essentially 3 times 10 to the 8, but we'll go with it. 2.9979, I think, times 10 to the 8 meters per second, about 186,000 miles per hour. So that is a constant, and that is a value that they do want you to know as you travel through. And apparently they would like you to know this number rather than 3 times 10 to the 8. So some people, a lot of people will use 3 times 10 to the 8. But here, I think they want you to use the 2.9979 number, something like that, times 10 to the 8. When we deal with electromagnetic radiation, we get this formula, which is an important formula. C is equal to the wavelength times the frequency. This is the speed of light. That is our wavelength in meters. And that is our frequency in reciprocal seconds. So I will say when you use this formula, you do typically need to make sure that your wavelength is in meters. And again, very commonly, especially if you're dealing with any type of color of light, a lot of time those are given in nanometers. So that conversion of nano, which is 10 to the minus 9, to meters is used a lot. And again, even centimeters occasionally, but I would say meters and nanometers very common for wavelengths, and going between those is really important. But when you do use this to make sure that it is in meters to cancel out correctly, and that's because the speed of light's in meters per second. So that is the unit that you need in this case. This is a formula that you could rearrange, and you can actually solve for any of those things. So the wavelength would be the speed of light divided by the frequency. The frequency would be the speed of light divided by the wavelength. So again, those are a couple of ways to sort of convert this guy into frequency or wavelength. Because C is a constant that you always have, as long as you know either the frequency or you know the wavelength, you can very easily calculate, obviously, the other thing, either the wavelength or the frequency. Any questions on that there? Why don't you try one? What is the frequency in reciprocal seconds for a wave that is 4.68 times 10 to the minus 7? Okay, so let's take a look. So we're looking for the frequency here. We have the wavelength, which is 4.68 times 10 to the minus 7. And we always have C, which is 2.9979 times 10 to the 8 meters per second. So if we look at our formula, C is equal to the wavelength times the frequency. Good news is it's the same calculation regardless of which one you're solving for. So we're just going to divide that to the other side. That will give us our frequency is C divided by our wavelength. In this case, our units are okay. They're both in meters. Once again, you do got to watch that because very commonly your wavelength is not always in meters. So got to make sure they are. So we're ready to plug in. We'll do our 2.9979 times 10 to the 8 meters per second divided by our wavelength of 4.68 times 10 to the minus 7. Clearly, we want to make sure that we do use our exponent button here. And if you do that, looks like 6.41 times 10 to the 14. The units here are reciprocal seconds. As again, the meters cancel, leaves us 1 over seconds when it's all done. 1 over seconds are hertz, right? 3 sig figs based off of the wavelength here. Any questions on that one there? Okay, so let's try another one here. What is the wavelength in nanometers for a wave with a frequency of 5.6 times 10 to the 14 hertz? Okay, let's take a look. So here we are looking for the wavelength. We have a frequency that is 5.6 times 10 to the 14 hertz. A reminder that 1 hertz is the same as a reciprocal second, which means that is 5.6 times 10 to the minus 14 reciprocal seconds. Again, we always have C, which is our 2.9979 times 10 to the 8 meters per second. So using our formula here, we will actually solve for wavelength in this case. Again, going to be very similar. Wavelength will equal C divided by frequency. That's going to be 2.9979 times 10 to the 8 meters per second divided by our 5.6 times 10 to the minus 14 reciprocal seconds. The seconds here will cancel, and that will leave us meters. And if you do that there, got 2.9979 to the 8 divided by 5.6 to the 14. Gonna get us no negative on that. That was just positive 14. So used to putting negatives. There we go. We got 5.35 times 10 to the minus 7 meters. This really has 2 sig figs, so maybe like 5.40 times 10 to the minus 7 meters. Once again, we are looking for the answer in nanometers. So nano is 10 to the minus 9, which means in 1 nanometer, there is 10 to the minus 9 meters. So that is the proper way to do that. We'll use that as a conversion factor. We'll put the meters on the bottom, which is 10 to the minus 9. That's basically 1 times 10 to the minus 9. The meters will cancel. So if we do that, maybe like a 540 nanometers here. Any question on that calculation? All right, so the good news is it's kind of the same calculation regardless of which one you have. And again, you always have that constant, not usually given to you in problems. So you got to remember that you always sort of have that available to you. Any questions on that there? So we've been talking about sort of electrons transitioning and these photons of light given off. And when these photons of light are given off as these electrons transition, they will fall somewhere on this electromagnetic spectrum. And this electromagnetic spectrum on the right-hand side here, we have a longer wavelength, which means we will have lower energy. This side is a much smaller wavelength, and that means higher energy. So down here at the longer wavelength, we got radio waves, which has enough energy there. Not to be too bad as we listen to our radio and we can move that through space. That's also why when you dial in a radio station, it's like 95.5 megahertz. Yes, it's a frequency, right, that you dial in to your radio station. If you go up a little further than that, past that is microwaves. Microwaves have a little bit more energy as the wavelength is getting smaller, has enough energy to move your water molecules super fast as you cook your pizza in your microwave, and your pizza's done in a couple of minutes because of that. Infrared is where we feel heat and energy sort of coming off. Then we have the visible part of the spectrum. The visible part of the spectrum, as we've been talking about, is where we have our colors. And again, our sort of Roy G. Biv here. And even within the colors, which are usually visible colors, are usually given in nanometers. As we talked about, the red side has the longer wavelength, so it's going to be less in energy versus the purple side there is going to have a smaller wavelength. That's where we see colors. So like in fireworks, when you shoot it off, they explode fireworks, excites the electrons to different energy levels. Depending on the elements there, you will see different colors coming off as they do the transitions. Also, like when we did the flame tests a while back, you put your sample in the flame, that is a lot of energy. That's going to excite all the electrons up to a higher energy level and come back down. And you see colors coming off there in the flame as a result of that. Ultraviolet is a little bit more energy past visible. That's why we put sunblock on so we don't get too burnt, right? As we go there, a little high in energy. X-rays are even higher in energy, much smaller wavelength. That's why they give you a lead vest when they give you an X-ray, right? And they leave the room usually, right? Because there's a lot of energy. And lastly, gamma rays are those radioactive rays, which are kind of like neutral, but they're just pure energy. So very, very high in energy, which is if you ever work with anything that's a gamma emitter, you should take a lot of precaution because it will give off a lot of energy as you do that. These are different parts of the electromagnetic spectrum. You do not need to know for my class here the exact break off, if you will, in terms of wavelengths, but you do need to know the order in terms of which one's higher in energy, lower in energy, longer wavelength, shorter wavelength of all these parts. That includes the colors as well, which one's higher in energy, lower in energy, higher frequency, lower frequency, longer wavelength, shorter wavelength. Any questions on that? All right, we'll lay it up there